These sounds produced by a skilled artist playing a sensitive and delicate instrument are what we think of as music. A scientist asked to define this music would say that it is essentially vibration, a complex of tones and overtones produced by the vibrations of the artist's instrument. And he might add that there are other vibrating objects in the universe and so other forms of music. The nucleus of an atom, for example, is a vibrating bundle of energy. Its vibrations have a characteristic pitch and a characteristic harmony some 50 octaves above what we can hear. This nucleus is the soprano of an atomic orchestra. The tenor range of our atomic orchestra is the tenuous shell of electrons which whirl with a characteristic vibration around the nucleus. When atoms group into the clusters called molecules, the entire molecule vibrates with a pitch corresponding to the baritone range of an orchestra. And the bass range comes from the vibrations of entire substances. Because its component parts are vibrating, all matter in the universe vibrates, producing a range of tones covering hundreds of octaves. There are strange and unexplored harmonies here, but for all their strangeness, these harmonies follow the same laws as the ones we are used to hearing in the sounds made by music. Just as a painting is an arrangement of paint on canvas, so is music an arrangement of vibrations in air. The sounds you are hearing are made by the vibrating string of the violin, which makes 768 vibrations each second to produce the tone G. The vibration is so swift that it cannot be seen except as a blur of motion. But we can slow the motion down with a special slow motion camera. This string is actually playing G 768 movements each second. Notice how the string beside it vibrates as well in what is called sympathetic resonance. We can study these resonances with an audio oscillator, an electronic device which will produce a sustained tone. The tone is fed to a loudspeaker, which will then set in resonance anything placed in contact with it. A string, when set vibrating at just the right number of vibrations per second, moves up and down in one big wave called the fundamental resonance. The pitch at which this fundamental resonance occurs depends upon the length of the string. A middle C string, for example, has a fundamental resonance of 256 vibrations per second. The string can also be made to resonate at a pitch twice as high as the fundamental resonance, called a harmonic resonance or overtone. The pitch of each overtone is always one octave higher than the one before. If we tune several strings so that the fundamental resonance of each corresponds to one overtone of the one above, we have a musical instrument capable of producing harmonious chords in one key. The octave interval, in other words, is produced by doubling the fundamental resonance of a string. You can actually see it happen on an oscilloscope. For example, we could begin with a tone produced by a string vibrating 256 times per second. This happens to be middle C. If we add this note to itself over and over again, we build up a series of tones, and these tones now form a simple scale. They are in the proportion of 1 is to 2, is to 3, is to 4, is to 5, is to 6. And they form a portion of our familiar musical scale. The important thing is the ratio of one resonance to another. As long as the tones have these even-numbered ratios, or something close, we think of them as musical. Our consonant chords are those made by combining certain tones that have these even ratios. A major triad, for example, has tones in the ratio of 3:4:5. All our common harmonies can thus be derived mathematically from the harmonics of a single string by combining vibrations in the proper ratios. We shall call this 1, 2, 3, 4 harmony. One-dimensional because the vibrating string out of which it is built has only one significant dimension, that of length. These one-dimensional harmonies have been known and studied since the time of Pythagoras, who concluded, by the way, that the entire universe followed these laws of proportion. He was not so far wrong, as we shall see. Now you are hearing not one-dimensional harmony, but two-dimensional harmony. Here's how it looks in slow motion. It is startling to realize that the head of the drum moves up and down 10 times between each beat of a roll. Because the vibrating object here is a two-dimensional membrane, not a string, it makes harmonics that do not obey the simple 1, 2, 3, 4 laws of ordinary harmony. Here, under controlled laboratory conditions, we can put a drum head through its paces just as we did with the string. Here is our laboratory version of a drum head in slow motion. This is the fundamental resonance in which the entire drum head moves up and down. The perfect pattern has been slightly mutilated because the heat of our lights has softened the rubber in places. Here's a harmonic, or overtone, corresponding to one of the overtones we saw on the string. Notice how there are now 2 waves on the drum head. Here's a higher harmonic with 4 waves. And here is an odd pattern that is basically 2 waves with some small ones intermingled at front and back. Where string resonances occurred at regular intervals, 1 octave apart, drum overtones occur at these fractional intervals. These other harmonies, or fractional overtones, are actually present in the sound of a drum, but they die away very quickly and are hard to hear unless the sound is electronically sustained. While the string is limited to one shape, and thus one pattern of overtones, we can change the shape of our membrane at will and produce an infinite number of harmonic patterns, in each of which the overtones develop at a different set of fractional intervals. Just as a membrane produces 2-dimensional harmony, so a solid will produce 3-dimensional harmony. And as you might expect, the pattern of resonance developed by a 3-dimensional vibrator is different from that developed by a string or a membrane. Where the string fundamental was one big wave, the drum fundamental a movement of the entire surface up and down, so the fundamental of a sphere is an expansion and contraction of the entire sphere. In slow motion, these vibrating spheres look like this. This movement is an overtone which occurs at a fractional interval above the fundamental. In this overtone, the sphere is resonating with 3 visible waves. Any resonance of a solid object is, as you can see, an actual contortion of the object's shape. In this still higher overtone, there are more waves, and each one is smaller than the ones we saw a moment ago. It is important to realize that you are not watching a loose cover flapping, but an actual vibration of the entire solid. String resonances have these ratios. Drum resonances these, and sphere resonances have these. Changing the shape of the solid means that the overtones appear at different fractional ratios, somewhat analogous to, but not identical with, the vibratory pattern of the sphere. Notice here how the top moves up and down. And here the waves ripple up the sides, making shoulders. Here's a still higher resonance with more waves, which make the solid shimmer like a hula dancer. There are consequently an infinite number of these three-dimensional harmonies, for each of an infinite number of shapes will produce a unique series of chords. The more complex our shape, the more complex the chord produced. And while we have a well-established mathematics to describe the harmonic pattern of a sphere, we have only the crudest mathematical tools to describe the shape harmonies of these. We can demonstrate, however, that a unique shape will produce a unique vibratory pattern, and we can even hear some of them. A completely unique shape has, of course, its own unique series of three-dimensional chords. If we could hear all the harmonies produced by a statue, we could recognize it from its sound alone, just as we can recognize a piece of music from its sound alone. If you could see the statue vibrate, it might look something like this. These three-dimensional harmonies are of great scientific interest, for they represent a portion of a harmonic pattern that underlies the universe. In particular, the pattern of harmonics developed by a sphere is of great interest because it is fundamentally the same as the pattern of harmonics developed by the atom. Just as a sphere displays a three-dimensional vibration, so the atom vibrates with what only can be called four-dimensional harmonies. The harmonics of a row of four-dimensional spheres would provide a kind of mathematical scale. And the fascinating thing is that this scale provides the complete basis of the periodic table of chemical elements. Each successive harmonic of a fourth-dimensional sphere, in other words, represents a rearrangement of the waves which compose the atom. Thus, within the last 20 years, we have come to the conclusion that the atom, far from being a little solar system, is actually a wave whose harmonic pattern is essentially that displayed by a vibrating sphere. If you could see one, it might look something like this. And if you could see a molecule, it would look like this, a wave pattern formed out of and containing the wave patterns of the atoms that compose it. Time was when light was considered to be a series of waves vibrating in a medium called the ether. We realize today that light is most accurately described as being a vibration pure and simple. In exactly the same way, the atom is not a particle that vibrates in space. It is the vibration. Our solid world is really only a wave of unimaginable complexity. All our language will allow us to say is that at heart, all matter is simply dynamic form. The truest statement is that matter is music. This is the pattern developed on an oscilloscope by the music of Johann Sebastian Bach. The reality of the music is in its dynamic form, the vibrations which are the music. If we translate those vibrations into grooves on a recording or into a vibrating phonograph needle, or into an oscilloscope trace, we are still speaking of the same pattern. This trace is just as much the fugue as the sound you hear. The two are indistinguishable in any real sense. By the same token, the statue is its harmonic pattern, a pattern that originated in the harmonies of the atomic wave forms that compose it. Out of such considerations of the fundamental reality of the universe comes a new perspective on art. The fundamental patterns of harmony underlying the universe have as much beauty, maybe even more beauty, than the one-dimensional harmonies we are used to. However, while we have known the mathematics for these multidimensional harmonies for 100 years, we know little or nothing about the psychology of them. Even though we may be intellectually convinced that an oscilloscope pattern is the same thing as Bach, will we ever react the same way to a vibration in air and a vibration in light? Why should the visual pattern alone be meaningless? When the audible pattern alone is far from meaningless. Why should this vibration in light mean more than the same thing in a different vibrating medium? It may be that the human ear is constructed in such a way as to make it difficult for us to perceive multidimensional harmonies, and we may not like them if we do hear them. That pleasant sound contains 2- and 3-dimensional harmonies and is acceptable, even interesting. The same sound spread out and reversed is neither acceptable nor interesting. There's no reason why the word vibration should be easier to apprehend this way, but it is. Thus it appears that unfolding these other harmonies may be a matter of opening up the right channels for understanding and enjoying them. And opening up those channels is, and always has been, a matter for an artist. All art is a matter of creating a unique vibrating form. The sculptor does it in stone or bronze. The painter creates a pattern of light vibrations. The musician does it through his instrument. And when we ask ourselves what the reality of imagination is, we realize that an idea is nothing but a harmonic pattern of brain waves. But it is, so far as we know, the only harmonic pattern to outlast the object that gave it birth.